Hello students, welcome to another lecture in the series of electrical circuits. Last time we were studying about current. Now in continuation with that, we are going to study about resistance and resistivity. So resistance, as we discussed earlier, it is the opposition to the flow of electrons. It's a property which is intrinsic of a material, right? All the materials they possess one or the other value of resistance, and it is denoted by capital R. And what's the formula? R is equal to rho L upon A, where L is the length of the object and A is the area. Rho is called resistivity. What is rho? Rho is the resistivity. Okay, so we will talk about resistivity in bit details. So here I want to give you an idea what we are talking about. So each of the material they have their own resistivity values. For example, this table over here shows you this sum of the conductors. For example, aluminium, what is the resistivity value? It is 2.82 into 10 to the power minus 8. So 10 to the power minus 8 is a very small number, right? 2.82. So as expected, conductors, they offer resistance, but the resistance is very less. The resistivity value is very less. So when we will put this resistivity value in this formula, rho L upon A, because rho is very small, right, 10 to the power minus 8, so any length or area it would give less value of resistance. That's why we use the metals in forming wires, okay, or where we need good flow of current. Similarly, if you pay attention over here in copper, gold, iron, mercury, right, all of these they have low resistivity values. And if we talk about semiconductors lie in between conductors and insulators. So as we all know, conductors, they are good conductors of electricity and heat. Insulators, they are poor conductor of heat and electricity. And the semiconductor forms in between, and they come in between. So carbon has the value of 3.5 into 10 to the power minus 5, and germanium has 0 0.5, and so on silicon. If we talk about insulator, if you pay attention over here, rubber, it has value of 10 to the power 13 to 10 to the power 16. And if you see over here, mica, teflon, wood, right, these are 10 to the power 10. So these are very large values. So if you see over here, um if we put this value over here, so no matter what length or area I'm taking, so rho value for wood, for mica, for rubber, it is very high, so the resistance will be very, very high. Okay, so these are values, they are around near 20 degrees Celsius. Okay, so they depend upon temperature as well. So moving on, so if we have a short wire, okay, with the large cross-sectional area. So let me write the formula over here. So R is equal to rho L upon A. So we are saying that if length is small and area is large, okay. So if length is small and area is large, okay. So what does that mean? This means that um, the resistance value will be less or high. It will be less, right? So they have smaller resistances. Large wire, so long wire, okay, and thin, long and thin wire, okay. So if I'm talking about long and thin wire, so what does that mean? So long means L value is large, thin means area is less. So if I rewrite this formula, R is equal to rho L upon A, because it's large wire, so length is going to be high, area is thin, so wire is thin, so area will be large, sorry, small. So this means that in this scenario, the resistance is going to be very, very high. However, in this scenario where length is small, area is high, the resistance is going to be very, very small. Okay, so wires that carry large current, such as main power cables, they are thick rather than thin. Okay, so now you understand why. Because they have to carry large current, and we don't want a lot of resistance in that. We don't want the energy to be wasted in overcoming the resistance. So we make the wires thick rather than thin wires, so we don't go for this side. So similarly, electrical tools that are used far away from wall sockets require thicker extension cords. So where you need to carry the current over larger distances, so we need the resistance to be small. So we will try to go with this specification where it should be thicker. Okay, the wire should be thicker in size. And moving on in this scenario, we have a question over here. So the question says, the instructions for an electrical lawn mower suggest that a 20 gauge extension cord can be used for distance up to 35 meter, but a thicker 16 gauge cord should be used for longer distances to keep the resistance of the wire as small as possible. The cross-sectional area of the 20 gauge wire is given 5.2 into 10 to the power minus 7 meter square, and for the 16 gauge wire it is 13 into 10 to the power minus 7 meter square. Determine the resistance. And we have to determine, there is a part. Determine the resistance of 35 meter of 20 gauge copper wire and 75 meter of 16 gauge copper wire. So let's start with the A. Okay, and if we go ahead and check the values from our previous table, that they are written here for us, because they have said here in the A part you have to use copper. And while using the formula R is equal to rho L upon A, you'll be requiring the rho value, the resistivity value. It is constant, and we don't expect you to learn that, so you can use that table. It will be given to you either in the form of table, or we will write it here in the question. Okay, so the row value from the table, it is 1.72. So I'm going to write here 1.72 into 10 to the power minus 8, because you can see, right, copper, it's metal, so its resistivity value is going to be very, very small. And moving on, what about length? Is it given to me? Yes. So he's asking me to find for 35 meters. So let's write that 35 meter. And what else? I need area. So they're saying over here, very nice, very beautifully, that 20 gauge wire has this much meter square. So meter square corresponds to the area, right? Cross-sectional area. So let me quickly write that 5.2 into 10 to the power minus 7. Feel free to stop over here and do the calculation on your own using this formula. So plugging in the numbers. So rho value is 1.72, L value is 35, and A value is 5.2. So let me punch in the numbers in the calculator. 1.72 into 10 to the power minus 8 times 35 times, upon 5.2 into 10 to the power minus 7. So it gives me 1.2 ohms. That's correct. Okay. Again, you can feel free to pause over here and try for the B part, which says 75 meter of 16 gauge copper wire. So since you notice over here it's copper, so the rho value is going to be same as for the A part. So rho value is 1.72 into 10 to the power minus 8. L is given to me 75 meter. I have to calculate for 75 meters. So let me quickly write over here. What is A? The area of cross section. So here it is given that it is 13 into 10 to the power minus 7 for 16 gauge copper wire. So let me write that 13 into 10 to the power minus 7. So what's the formula we are going to use? R is equal to rho L upon A. So rho value is 1.72 into 10 to the power minus 8. L value is 75, and A is in the denominator, and its value is 13 into 10 to the power minus 7. So when putting in the calculator, let me quickly do that. 1.72 into 10 to the power minus 8 times 75 upon 13 into 10 to the power minus 7. Okay, so we are getting 0.99 ohms as my answer. Okay, if you go ahead and compare the values of the resistance. Okay, so even though it is more than twice as long, the thicker 16 gauge wire has less resistance. Okay, so if you pay attention on the numbers over here, even though it is more than twice as long. So this is 75 meters, okay? But if you pay attention on the area is 13 into 10 to the power minus 7 as compared to 5.2 into 10 to the power minus 7. So this wire is thicker. So even though it is very very long, but because it is thick, so what happens? The resistance is less. So that means it is safe to use thicker wires for longer for carrying the current to the longer distances, because in that case, even though the length is larger as compared to other wires, but because the area is more, so the resistance is going to be less. I hope that makes sense. So here is a quick application where we can use resistance in medical field. So it's find its use in so many areas, in so many doing analysis, doing tests. So one of the example is written over here. So what we do over here is this is called impedance or resistance lethysmography. Okay, so excuse me for mispronouncing that. So here is a figure that shows the technique which is used to diagnose the blood clotting in the vein. So basically this thing is used to determine whether there is a clotting in the veins, there is a blood clot or not. Okay, so here it is done near the knee area, as you can see in the diagram. So here is a pressure cuff, okay, which is used to measure the blood pressure measurements. So it is placed here in the mid thigh area. So the electrodes which you see over here, okay, the blue color electrodes, they're attached around the cuff. So the two outer electrodes are connected to a source that supplies a small amount of AC current. So these two electrodes, they are connected to this source, this battery, which is the source of AC current, a very small AC current. And if you pay attention on the two inner electrodes, so these are your outer electrodes and these are your two inner electrodes. So they are separated by some distance L, okay? So this is your AC current source. So here these are the outer ones, okay? So these are separated by some distance. So what happens is, so the two electrodes are separated by distance, let's say, which is L, and the voltage divided by the current gives us resistance. So voltage divided by current will give us the resistance. So what's the key technique over here? So the fact that the resistance can be related to the volume of the calf area, right? So you saw the leg, right? So the calf area where we are placing your electrodes. So if you look at the formula, R is equal to rho L upon A. Area is, can I write volume is equal to area multiplied by length? Yes, so volume can be written like this. So if I isolate A over here, it will be V upon L. Do you agree? So I'm just going to quickly do that. Instead of A, I'm going to write V upon L, right? So if I rearrange this, so it will become rho L square upon V. Okay, so this is what we have over here. Now the resistance, if you see, it is inversely proportional to volume. So resistance is here, resistance is inversely proportional to V. V is in the denominator, right? So if this is a fact that is exploited in diagnosing that whether there is a clot present in the body or the veins or not. So what happens is, because the blood is flowing from the heart into the calf through the arteries in the leg. So let's say this is the leg, okay? So we were talking about sorry, there was some technical fault. So the pressure cuff, which we had over here around the mid thigh area. So we inflate that to the point that the venous flow, it stops. Okay, the blood flow through the veins, it stops, but the flow through the arteries, Okay, the blood flow through the arteries is still there. So that means that the blood is entering, okay, the calf area, but it is not leaving. So as a result of that, volume will increase. Okay, do you agree? So the volume will increase because through the arteries the blood is allowed to enter, but through the veins it is not allowed to go out. So because volume increases, so because there is a reversal relationship, R is equal to rho L square upon V. Because the volume is increasing, resistance will decrease, right? So then after some time, what we do, the cuff pressure which we have over here over the mid thigh area, we let it go, we remove it suddenly. Okay, so what will happen? So the blood through the veins will automatically will start flowing backwards. Okay, and as a result the volume will resume its original value, right? And so does your resistance, right? So if the person is healthy, okay, the veins are unclotted, there will be a rapid return to the normal values. Okay, however, if there is a slow return, okay, the return is slow, that denotes that there is a presence of clotting. Okay, so this is how the blood clots are detected. Now moving on, let me clear this up. So the resistivity of a material, we were talking about resistivity. Okay, we know that R is equal to rho L upon A. So resistance not only depends upon the length of the material, not only depends upon the area of the material, but this is resistivity. So I told you that we will talk in detail. So the resistivity of a material depends on the temperature. So you remember I showed you the table, and underneath that table we wrote that it is these values, they are indicate they are around 20 degrees Celsius. So because resistivity is temperature dependent, and this is how it is dependent on temperature. So how this formula it got derived, we don't need to go into that much detail. We want to understand a little bit of the theory around it. In metals, the resistivity increases with increasing temperature. Okay, so if you start increasing the temperature, the resistivity value will also increase. In semiconductors, the reverse is true. So if you increase the temperature, resistivity decreases. So this is true for the semiconductors. This could be asked on the exam as well. For many materials and limited temperature ranges, it is possible that we can write this simple formula: R is equal to rho naught 1 plus alpha T minus T naught. Okay, so rho and rho naught, they are the values of the resistivity at temperatures T and T naught. Okay, so these are the values at temperatures T and T naught. And if you talk about alpha, alpha has the units of reciprocal of the temperature. Okay, it is also called the temperature coefficient of resistivity. So alpha is the temperature coefficient of resistivity. Okay, and when the resistivity decreases with increasing temperature, alpha is negative. So when we just said that resistivity is increasing and the temperature is decreasing, right? So when there is, sorry, when the let's say both are going up, right? Resistivity is increasing with the increasing temperature, so alpha will have a positive value. Okay, let's say the reverse is true, resistivity decreases, temperature is increasing, so alpha value will be negative. So this could be also asked in one or the other way. So you should be able to keep that in mind. And um if you do this, resistance is given by R is equal to rho L upon A. Okay, if you multiply both sides by L upon A, let me do that for you. So if I multiply over here L upon A and multiply over here, so if I'm doing something on this side, I have to do the same thing on this side. So if I remember, R is equal to rho L upon A, so getting rid of this, I can write, because I just multiplied by L upon A, I can call it as R, and this side can be referred to as R naught, right? So this is also true, which is written over here. R is equal to R naught 1 plus alpha T minus T naught. Okay. So you can see accordingly that if there is a question, what kind of formula you want to use. And let's go ahead and practice over here this question. And we're almost done with the topic of resistance and resistivity. So here there is a heating element on an electric stove. So you must have seen that. um, so the element contains a wire. Okay, let's say its length is 1.1 meters. So you must have seen electrical coils on the stoves, which become red hot when you turn on the stove, right? So that wire that runs through that, let's say its length is 1.1 meter, area is 3.1 into 10 to the power minus 6 meter square, through which electrical charge flows. So the wire is embedded with an electrically insulating material that is contained within a metal case. So you will put this inside a metal case. The wire becomes hot in response to the flowing of charge. So when you turn on the stove, so the charge starts flowing, and it starts to become heated. It starts becoming hot. So the material has a resistivity. So let me write down what's given to us. Let me write the given piece of information. So I can see length is given to me, area is given to me 3.1 into 10 to the power minus 6 meters square, and then what else is given to me? Rho naught value. Okay, rho naught is equal to 6.8 into 10 to the power minus 5 ohm meter, and the temperature. So this is the resistivity value corresponding to this temperature. So rho naught at T naught is equal to 320 degrees Celsius. Makes sense? And a temperature coefficient of alpha of resistivity, sorry, okay, alpha is also given to me, 2 into 10 to the power minus 3 per degree Celsius. Okay, now determine the resistance of the heater at an operating temperature of 420 degrees Celsius. So at 420 degrees Celsius, what I have to determine the resistance. So I have to determine the resistance. Okay, so what we can do is you can do this question in two ways, because I just told you this formula. R is equal to R naught 1 plus alpha T minus T naught, right? So first you can go ahead and find a rho naught, and come back here, and you can fill in the numbers. Okay, and also you can follow this procedure. Let's say we have this thing. So let's first of all find rho. Okay, because I have to find R, and R is equal to rho L upon A, right? But rho is not here. Okay, so I have to find L is given to me, A is given to me. So how I can find rho? So rho I can find using this formula, rho naught 1 plus alpha T minus T naught. So this you will do, right? So let's see. Rho naught is, let me just clear this up over here a little bit. Okay, so let me quickly show you. Mm, So rho naught value is 6.8 into 10 to the power minus 5, and then there is a bracket, then there is 1 plus, and then alpha value is 2 into 10 to the power minus 3, and the bracket 420 minus 320, right? T minus T naught, right? So how will you solve it? Let me do that simplification a little bit. Okay, so first you can do is you can simplify over here. So I will write 6.8 into 10 to the power minus 5 is outside, 1 plus 2 into 10 to the power minus 3 I have, 420 minus 320 gives me 100, right? So, and again I can simplify a little bit, 1 plus 2 into 10 to the power minus 3 times 10 to the power 2. Let me write it in this form. So 100 can be written as 10 to the power 2, right? So I have 10 to the power minus 3 times 10 to the power 2. We have already discussed in our previous videos 10 to the power a times 10 to the power b. What's the formula? A plus b, right? So I have over here a as my minus 3. So let me substitute that. And this is plus 2. So 10 to the power, I have 2 into 10 to the power minus 1, right? And 2 into 10 to the power minus 1, can I write it as 0.2, right? So I can move to the decimal one place on the left hand side. So 1 plus 0.2, can I write it as, let's say, 1.2? Let me write it like this. So let's simplify a little bit. Now you're good to go. You can multiply these two numbers, 6.8 into 10 to the power minus 5 times 1.2. And this comes out to be 8.2 into 10 to the power minus 5. So what we got over here, let me write that. So we were solving for rho because that was the missing ingredient, because we want to find r, or rho was missing. So rho came out to be 8.2 into 10 to the power minus 5. Do you know length? Yes, it is 1.1. Let's quickly write that. And then, do you know area? Because in the denominator I need to fill an area. So 3.1 into 10 to the power minus 6. Let's put this thing in the calculator. By the way, this is 1.1. So 8.2 times 1.1 times 10 to the power minus 5, okay, is equal to, and then divide by 3.1 into 10 to the power minus 6. So you got 29 ohms as your answer. Make sense? So you can feel free to, drop the questions. I will be happy to answer them. Thank you. This is it for this one.